All right, well, we're done with our chatter. Welcome back to IUP Geoscience Day. This is our 46th Geoscience Day. We've been doing this every year for close to half a century. So we aren't going to let unusual circumstances put us out of commission. We thank everyone who's taken the extra effort to join us today. We have an afternoon session now on stratigraphy and paleontology and climate and paleoceanography. And so the first talk we're going to go through was submitted by one of our students who is not able to use the live internet feed. This has been a challenge for many people these last few weeks. And so I will be in charge of playing this talk back. I will do my very best to push all the right buttons, but we're downloading and uploading a file at the same time. So we will do our very best. To do that, I need to do a couple of things, so bear with me for a couple of seconds. And we'll be having a talk by Mitchell Moore, who will talk about environmental determination for paleoecological reconstruction at Jurassic National Monument.
Hi, my name is Mitchell Moore, and I've been conducting environmental determination for paleoecological reconstruction of Jurassic National Monument. Over the past 2 summers, I've been dedicating my time and energy into volunteering so I can be a part of such an amazing project. During my time engaging in my undergraduate research, I've had the honor of working at the Cleveland Lloyd Dinosaur Quarry, which is just known as Jurassic National Monument as of 2019. It's worked on by many academic institutions, ranging from Utah University, who originally worked on it, to Princeton University that worked on it in the late 1900s. As of right now, there are only 2 licensed research teams able to work on premises. They are Indiana University, Pennsylvania, being led by Dr. Jonathan Warnock, and University of Wisconsin-Oshkosh, led by Dr. Joe Peterson. This site dates back to 147 million years ago during the Jurassic period, which is known for its semi-arid climate, and it is very unique in its differentiation of stratigraphy and fossil assemblage compared to other sites in the Upper Morrison Formation. This brings us to a very unique fossil assemblage of the Jurassic National Monument that sets it apart from other Upper Morrison Formation bone beds. The predator-prey ratio of 3:1 is dominated by Allosaurus fragilis, which are mainly found in their adolescent age, shown by the tooth on your right, which has serrated edges, which are characteristic of a youth allosaur based on the small size and lack of bite power that they possess. The serrated teeth gave them upper hand on bigger prey so that smaller adolescent allosauruses can be an independent predator. Other taxonomically distinct groups have been found here, such as sauropods and theropods. Theropods ranging from Torvosaur, Ceratosaurus, and Allosaurus. Sauropods were found here ranging from Camptosaur and Camarasaur. On the right, you can see us looking at a newly discovered site about a mile away from the actual quarry site itself. This quarry site was found by Dr. Peterson and Dr. Warnock while out on an expedition. Our work there discovered that there is an articulated vertebrae of a sauropod. Understanding the environmental history of Jurassic National Monument is a very important stepping stone when forming an understanding of Upper Morrison bone bed formations. This bone bed formation is very unique in its predator-prey ratio that it contains, but the lack of bite marks that we find on bones. The more characteristics that we find on bones are water damage and decay from uh, higher and lower velocity stream flows. These stream flows caused by the semi-arid climate of the Jurassic period are very reminiscent of an ephemeral stream environment caused by climatic alterations in precipitation content. The higher the precipitation content, the higher the velocity flow is, the more it can move downstream. The thick layers of the deposited limestone that cap the bone assemblage in the quarry are close to a half-meter thick using the glue jar as a scale. This caps the quarry, and underneath that there are different layers of mud and claystone. This shows a lake bed that changes over time, and the limestone was formed through a very large interior lake environment that seemed to spread miles to wherever the limestone ends at. The semi-arid climate of the Jurassic period lent its hand to an erosive alternating layers of red, gray, and purple silt to the less erosive layers limestone, sandstone, claystone, and mudstone. These alternating layers do a great job at characterizing this unique fossil assemblage and giving an insight into the past of how these fossils were really deposited. To properly analyze the environment to determine paleoecological reconstruction of Jurassic National Monument, we needed to focus on the stratigraphy of the area to get a full grasp on the environmental history. To do so, we measured the stratigraphy with a Jacob staff and a Brunt compass. The Jacob staff is a pole that is no longer than 1.5 meters, separated into 10 centimeter increments. With the Brunt compass on top, we measured the attitude of the rocks, even though a lot of them measured just vertically with very low gradient to them. We obtained physical rock samples to construct physical stratigraphic columns to help picture them instead of just having two-dimensional columns on paper. We chemically analyzed limestone samples with a scanning electron microscope. This gave us the elemental content by percentage of weight, with an idea of looking at the heavy metal content of the limestone in the quarry to see if the geochemistry is at all different from the other samples, the other three samples that we took from across the quarry. We also gridded and mapped excavation sites so that we can register the bones individually and get a count on them. Research at the Jurassic National Monument is consisting of geochemical analysis on the limestone. On the picture to the right, you can see an example of what this limestone looks like, physical characteristics of it, and how thick it really is. Also, we focus on stratigraphy, which can be shown through the Jacob staff and the rock hammer, which were the instruments used to determine the thickness and composition of the limestone and other stratigraphy around the quarry. The aerial drone imagery we did really helped us with visualizing where the limestone samples were taken from and where exactly I did my strat columns. I also wanted to show people that couldn't be in the quarry exactly what the environment looked like and where we took the limestone samples from. The two claws on the right, you will see, have two different weathering profiles, which can be shown through the presence of a tip and fully articulation on the top one, which has a very quality weathering profile with characteristics of it not being reworked by higher velocity streamflow, but instead deposited at a very calm entry point into the interior lake that is known as the quarry. The second weathering profile on the bottom claw is much different. It doesn't have a tip to it, and it is in the limestone layer that was deposited and then picked up and reworked by higher velocity flow and then deposited, giving it the abrasions that you see to the right. To determine the paleoecological reconstruction of Jurassic National Monument, we needed an abundance of macrofossils which can be found as lake sediments in this environment. The environmental history of this area can be shown through the two-dimensional imagery that we produced over the 2 years of research. Above, you will see the stratigraphic columns, and to the right, you will see the key used to help guide you. The correlating layers that run across the quarry are very important for defining this area as a paleo environment. The limestone layer that runs across the quarry and encases the bone assemblage is the micritic limestone that oxidizes orange. The other reminiscent bed that is very age constraining is the bentonite ash layer that was deposited during a tertiary era volcano. This alteration in siltstone will give you an environment that fluctuated in precipitation content through climatic alterations in that environment. This environment has sustained a semi-arid climate of the Jurassic period, and this stratigraphy shows that this was an ephemeral stream environment that deposited an interior lake and came with it a large amount of dinosaur fossils. The reason for my experiments conducted at Jurassic National Monument were to gather supporting evidence of our hypothesis that Jurassic National Monument is a drought-induced fossil assemblage affected by the cyclical weather changes during the Jurassic period. The results concluded from the geochemical analysis of the 3 limestone samples yielded a very interesting sight when noticed that the limestone sample from the quarry that the bones were deposited in also had a content showing higher percentage of nickel, iron, and magnesium. These higher percentage of heavy element contents could be contributed from the leaching out of the elements from the dinosaur bones. Right now, that is not what our focus was of this research, but will be looked at when doing further work. Right now, the stratigraphy that you see, the two-dimensional imagery showing the physical characteristics of the ephemeral stream environment that deposited the quarry, the alternating layers of gray, purple, and red siltstone, along with the underlying layers of clay, mudstone, limestone, and sandstone, all are very characteristic of an ephemeral stream environment deposited late 147 million years ago. Would be possible if it wasn't for Dr. Warnock extending the initial invitation to me my sophomore year. Without him, my geological interests may never been sparked, and I'm not entirely sure what I'd be doing right now. The volunteer opportunity that he gave me at Jurassic National Monument when it was Cleveland Lloyd Dinosaur Quarry made my life amazing and produced me to be who I am today. I greatly appreciate Justin Petrico for showing me the ropes last year when it was my first year at the quarry. He really paved the way for my interest in paleontology. I'm really thankful for Dr. Peterson for taking me and showing me really how to be a field geologist and a good worker. Also, I owe a lot to Dave Hall and Steve Clausen, who were brothers to me at the time and still are when we plan to go out into Utah next. I also thank Colin for committing to taking the drive with me in 2019. And
This is Professor Coles back again. That is where the audio cut off right at the end of the credits, but we hope all those who are credited saw their names on the slides. I don't believe we have Mitch Moore with us. If anyone, of course, people in the Zoom room who may have questions can know how to transmit them. And I imagine if Professor Farnsworth got any questions on YouTube, that she can collect those and we can pass them along and see if we can send you some answers. The last two talks of the day will be given by our speakers who are with us. We're going to take about 4 minutes to take a short break, and the professors will catch up on their paperwork, and we'll be back in about 3 or 4 minutes for the next talk. Hello, everyone. Welcome again to the 46th Geoscience Day at Indiana University of Pennsylvania. We have now several talks for you on the record of climate and ocean circulation and global conditions as recorded in the oceans. Our next talk will be given by Shane Parker, who's studying the effect of Western Antarctic ice sheet collapse on nutrient recycling rates during marine isotope stage 31. Shane, are you ready?
Yep, I'm ready to roll.
Okay, well, I will release the video and we'll let you share your desktop and your screen and give us your talk.
Alrighty, so my name is Shane Parker, and I'll be presenting the research that I've done over the past few years on the effects of an ice sheet collapse and how an event like this in our past could actually influence global systems. So first, let's start by actually stepping through the actual area of study. This took place in the Southern Ocean, which is the water that surrounds Antarctica, and it's capped by the 6 degrees south latitude line, which is roughly where warmer subantarctic waters begin to mix with the colder Antarctic waters. Now, Antarctica itself is covered in ice and can be split into two, West and East Antarctica, with the mountain range splitting in between. And the ice makes up about 60% of Earth's total fresh water, with West Antarctica making about 10% of that. So I looked at West, the landmass or the land is covered by a good percentage of ice shelf volume, which means that it's underlined by water and not by land. This fact in itself makes it more susceptible to changing climate and warming water temperatures. It's more likely to be etched and eroded. So this study was done in light of our own current changing climate and trying to understand what lies in the future. Now, in order to better model the future, we have to go back and look at the past and understand the drivers of the past. We can actually look back at our recent past in 2003, when we saw the large Larsen B ice shelf collapse, which is actually captioned up here on the screen. So this ice mass is about the size of Rhode Island, and it took place over 3 months for this decay, just to give you a scale. So this concept links back to my study in that everything is going to be interconnected, and we're looking at a decay over the course of thousands of years. And as we could imagine, it could impact ecosystems locally and then eventually on a global scale. So the Southern Ocean is home to a lot of microorganisms, and including diatoms are the main organisms in this environment. They are key to primary productivity. They make up about 20% of it, and they are a single-celled algae. They make hard shells out of opal. They're microscopic, and they're photosynthetic. So their primary productivity makes them a key component in the food web. So if they're to be altered in any way, it could have a serious bottom-up effect. Now, the silicate acid leakage hypothesis, this is kind of a side note. My study could be a smaller part to actually prove and support this greater idea, which is that there's a constant competition between siliceous organisms and calcareous ones. So these siliceous diatoms, when they're able to outcompete these coccoliths, which are making calcium carbonate shells, now, in order to produce calcium carbonate, we have to also produce CO2 at the same time. So when you multiply this over trillions of these organisms, you could actually be influencing the atmosphere. And as we all know, CO2 is a greenhouse gas, and any alteration in that could have a serious effect on climate. So my study is a bit smaller, but it could actually lead into supporting evidence for an even larger theory like this. Now, let's get into specifics here. I looked at a sediment core taken off the tip of South Africa, and I looked at it under microscope to try to understand the past about 1 million years ago, this time phase known as marine isotope stage 31. Now, this chart here is modeling the present, and we are stepping back in the past as we go along this axis. Now, these high peaks, it can almost be viewed as a thermostat. The high peaks are the higher temperatures, and then the lower peaks are the glacial periods. I looked at this peak here, which is substantially higher than some of the local ones, and it's known as marine isotope stage 31, which is an interglacial. So diatoms were preserved in this sediment as glass shells. And once they're viewed under a microscope, they're actually useful as proxies, as an indirect measure of climate in the past. Now, typically, diatoms are used to model glacial and interglacial cycles, whereby iron, when it's flushed in by, say, a glacial till process or by wind-blown dust, iron acts as a fertilizer for these diatoms, and it actually thins the shell as they expand fast. So during times of less iron flux, these shells are thicker. And it's important to understand that diatoms actually only live around 6 days. They're very sensitive to their environment. And we can actually see in the microscope slides and measure ratios known as silica to nitrogen ratios, which is a measure of silica, which is capturing the hard parts or the shell, to nitrogen, which is basically covering the organic matter, the softer parts. So when we have a flush ratio of 1:1 like this, we're seeing thinner shells. And then when we have something larger, like 4:1, we're seeing thicker shells. Now, marine isotope stage 31 is a bit different because it's an interglacial where there's a hypothesized period of ice sheet collapse. So whereas before we would see glacial till washing in iron or wind-blown sediment, we might expect in marine isotope stage 31, which is what we're hypothesizing, is that an ice sheet collapse could actually be the driver of more iron in the water, more fertilization effect. And since we know that these shells thin when iron is in the water, we can also gauge that there's going to be more surface area exposed to the water, which means they're going to be more likely to dissolve. So not only is the preservation of these diatoms a proxy for iron in the water, it's now a proxy for dissolved silica leaking off of the diatoms. So here's a simple schematic of what I expected to find throughout my study. Before, I'm looking at, this is core data that is taken further down in the core, and it's capturing a time period before the ice sheet collapse. Now, before the ice sheet collapses, we'd expect to see those thicker diatoms because there's less iron in the water. And then as iron begins to flush in, as the ice sheet's collapsing and things are heating up, this, by the way, this red area is marine isotope stage 31 when things are heating. And we'd expect to see more iron, more fertilization, and then these diatoms begin to thin and shrink, and their shells are now dissolving, becoming less preserved. And then as things return back to normal, we'd see the thicker diatoms again and better preservation. So this axis showing well preserved, poorly preserved. I used a method known as preservational binning to collect my data. It's a simple technique whereby I looked in sediment under microscope for a specific species known as F. Kerguelensis, which is this guy right here. And I looked for 50 individuals per slide. I cataloged them into 3 basic groups known as good, intermediate, or poor preservation. And then from there, I could use these tallies to generate a level of preservation. And this preservation value could be mapped along depth and time. So this is a lot to look at, but I'm going to try to step you through it. This is my data in the black that I collected. And these lines over here are other proxies that are showing, for instance, red is a proxy for warmer weather or warmer climate and warmer water species. So here, let's see, let's start with the purple. So the purple is my marine isotope stage 31. So if we look back at what I expect to see, this is my marine isotope stage 31. We'd expect to see a dip in preservation as iron is flowing into the water from the ice sheet collapse, which is what we start to see here actually. So we see a dip in preservation. And here, this proxy is actually a proxy for high primary productivity. So this lines up quite well actually with the dip in preservation values. My guess is that as we're experiencing the ice sheet collapse, we'd also be experiencing higher productivity near the shelf because more nutrients are now available. So we'd expect to see a peak here, which is also lining up with this peak here. Now, these blue ones, by the way, are proxies for colder weather. So we'd expect to see, obviously, very little colder species in this time period. And then this highlighted region is a isolation maximum. So the hottest it would have gotten prior to marine isotope stage 31 and a little bit into it. Now, after all is said and done, I was able to confirm actually that and back my hypothesis that in fact, when we experience an ice sheet collapse, a West Antarctic ice sheet collapse, we would in fact experience more nutrient recycling, as is made evident by this dip in the data, whereby these diatoms are becoming less preserved because they're thinning, and that thinning is due, or that thinning is thereby creating more nutrients and more access to dissolution. So, also, I've been kind of creating a website during this down spare time to publish some of this original data because I knew it was pretty hard to find a lot of these data points actually. So that's my contribution. And I'd like to give a thank you for everybody that made this possible, all the faculty and staff, in particular, Dr. Warnock really stepped me through everything. It's just an all-around good guy to be around. And so thank you. And it's been a good ride.
All right, thank you, Shane, for a great presentation. Let's check around the room and see if we have questions for you. Dr. Hovind.
Hey, Shane, nice job on the talk. I was wondering if you could sort of walk me through the mechanism by which an ice sheet collapse provides more nutrients, because I thought it was mostly ice on water. So where are the nutrients coming from when that ice sheet collapsed? So that was the first question. The second question I had for you is related.
Right. So I think the sense of confusion that I'm hearing is that so the ice sheet is going to be over that land mass. Maybe perhaps ice shelf is confusing in this matter because the ice shelf would be over the water, but the ice sheet itself would be, I guess it would be recharging and then pushing sediment down. And then as it's retreating, then we could be experiencing that.
Okay, so it's coming from
actual flush of
off of land.
Yeah, it's still Terrigenous input. It's not the ice shelf.
Okay,
it's an ice sheet.
Yeah, I was misunderstanding there. But the question I have for you then is how do you disentangle the possibility of additional nutrients or iron input from the ice shelf, ice sheet through the collapse, presumably because of a climate-induced change to the temperature, from other sort of climate variables like increased runoff or changes in the iron input from aeolian processes?
Yeah, right. So I think that would actually be best answered by comparing even more proxies, perhaps some that I'm not even aware of. I just have a small toolkit here, honestly, of warm and cold proxies, and then this one here of the primary productivity. So that's kind of what I'm using to line up things. But definitely a better suite of proxies would help hone in on things and cancel out variables.
Okay.
Dr. Lewis?
Yeah, Shane, that was great. I enjoyed that. You alluded to the sort of the trend to the left, because I don't know how to use this language, of your data at the beginning of marine isotope stage 31, but it looks like then there's a kind of a quick recovery well before the end of the stage. Is that, do you have some sense for what that means, or am I misreading the plot?
Yeah, so there is a quicker recovery. So I mean, my thought is that as the ice shelf collapse or the ice sheet collapse reaches its maximum, there's really not much else to. Well, it's really the ice at that point has retreated to a point where it's really not flushing out much nutrient. I mean, once the sheet itself is shrunk, it's really not there to add to the water.
So in that case, I guess the nutrients are really within the ice that's being lost, and once the ice is gone, that nutrient flux is cut off, is what I think what you're saying.
Yeah, I mean, it could be either way. I mean, the ice could be a driver of it, or it could be within the ice.
Okay.
It would be hard to say.
Okay, thank you.
Let me check with Dr. Farnsworth to see if there are any questions.
There are no questions from YouTube.
All right, thank you. I'll take one last look around the room here, which takes me a moment. I have to go through 4 screenfuls of colleagues and students here. All right, I think we'll ask Shane to imagine hearty applause, and we have a few minutes before our next talk, so we'll be back shortly before 1:40 Eastern time. Hello, everyone. This is Geoscience Day at Indiana University of Pennsylvania. I had a chance to step away from my camera and check YouTube, and we just discovered that if you're going to ask a question on YouTube, you have to be succinct. It looks like you run out after a couple of hundred characters. So we'll keep an eye on that for you and do our best to pass along questions about the next talks. Our next talk, continuing our look at paleoceanography, is by Victoria Lewis, determining the impacts of paleoclimate change on oceanic nutrient conditions. And let me check and be sure Victoria is ready to start.
Yeah, I'm here.
Okay, I'll stop my video and turn it over to you.
All right. All right. Hello, everyone. My name is Victoria Lewis, and it is truly a pleasure to be able to share my undergraduate research with you. The title of my research is Determining the Impacts of Paleoclimate Changes on Oceanic Nutrient Conditions with the Use of Diatom Records. And I'm well aware that's a bit of a mouthful, so I'd like to break it down for you. Paleoclimate changes in this context is really just referring to glacial and interglacial cycles. Oceanic nutrient conditions are talking specifically about iron concentrations within the Southern Ocean, and diatom records will refer to preserved diatoms within the sedimentary core sample that I used throughout this research. And no worries, we'll be digging further into all of these throughout the research. So what are diatoms and why should you care about diatom or paleoclimate research? Well, paleoclimate research actually remains very relevant to our everyday lives and potentially our future lives as well. So I tried to break it down into three main reasons, although I'm sure there's plenty more. Diatoms, first off, are carbon fixators, and so they're able to remove carbon dioxide from the Earth's atmosphere by breaking down carbon dioxide into the two bare components of carbon and oxygen. After this, they're able to re-emit the oxygen into our oceans and atmospheres as clean air for us to breathe. And there are actually some rough estimates that diatoms provide about 50% of the clean air that you and I breathe every day. Diatoms and sedimentary core records also provide us with clues about past conditions of previous climates. And these climates could be more extreme or similar to the environment that we have today. But either way, this is going to provide us with insight into what we have to look forward to as the Earth is rapidly changing and the environment is constantly changing. And with a growing concern about carbon dioxide and greenhouse gases within our atmosphere, both of these points really sold me on this research, as it could be potentially used to mitigate these greenhouse gas issues. If that's not enough to sell you on diatom research, diatoms actually have the ability to affect the oceanic food chain all the way to the point that it affects us humans. So diatoms are primary producers. They rely on the sun, but shrimp rely on the diatoms, fish rely on the shrimp, et cetera, all the way down to us. And so when there's one small impact on diatoms, this has the ability to affect an entire ecosystem worth of organisms, and then eventually the pockets of those people who rely on fishing as a source of income and to provide their livelihood. Global iron concentrations are actually controlled by several variables, and I decided to include this entire graphic because it does a pretty decent job of summing up total iron input, output, and transfers. But what I'd like to draw your attention to for this research is really just these red rectangles. And so during interglacial periods, we have iron input from aeolian wind as well as glacial runoff and melting. And so basically more barren land during these interglacial periods allows sediment and dust as well as iron to be transferred into the ocean as well as the atmosphere. And once in the atmosphere, it's able to be deposited into these glaciers and icebergs. Again, since it is during an interglacial period, these higher temperatures allow for runoff and melting from the glaciers and the icebergs, which allows input into the ocean and more iron availability for these plankton down here. Again, the plankton down in this red rectangle really just refers to the diatoms. It's nothing special. During glacial periods, we would suspect lower iron availability within the oceans, just due to the fact that there's less terrestrial land that is uncovered by ice, and there's not really as much runoff and melting. All of this sediment is just kind of being taken up and frozen within these glaciers and icebergs. And that really leads us nicely into the hypothesis, which is that diatom morphology will reveal changing iron conditions due to paleoclimate changes. And with this hypothesis, we really want to see two ends of a very extreme spectrum. And so at the very top, we see the first end of this spectrum, which is a shorter, stouter, and unhealthier diatom. And because of this morphology and this change in shape, we would suspect that this is revealing lower iron conditions within the ocean and in turn a glacial period. The other end of the spectrum is a longer, skinnier, and healthier diatom, which again, we would suspect reveals a higher iron availability within the ocean and an interglacial period. Very briefly, I'd like to touch on core PS58-54, which provides the setting for this research. So this core was drilled off the western coast of Antarctica within the Southern Ocean and the Amundsen Sea, and it was cored aboard the RV Polarstern set forth by the Alfred Wegener Institute in the early 2000s. The core itself spans about 1.2 million years, and the sediments range in age from 27 to 900,000 years old, which is during the late Pleistocene. I would just briefly like to say that I only did a fraction of the core, so the sediments in my region only span an age from 50 to 450,000 years old. Now, my methodology was very simple and straightforward. Smear slides were created by Dr. Jonathan Warnock from sediment that was cored from core PS58-54, and I was able to analyze these smear slides beneath a microscope. And so each slide represents a 10 centimeter interval in depth. And when I was looking at each slide, I was looking for preserved and intact diatoms. And once I would find a diatom, I measured it, the length of it at its longest point, and then the width of the diatom at its widest point. And I would really just input that into an Excel spreadsheet. It's nothing special. And for each slide as well, I would look for about 50 diatoms to ensure a very fair sample size. And so 50 diatoms per slide and 74 slides. If you're not keeping up with the math, that's okay. It totals to a little over 3,000 diatoms that were subject to this analysis. After I input everything into this Excel spreadsheet, that's when I got to move to the fun part, which was the data synthesis. And the results from this data synthesis actually yield some unexpected outcomes. So with the data that I collected about diatom size and then age and abundance data from Dr. Matthew Converse, I was able to put together this graphic. And if you look at the x-axis, this represents age in thousands of years before present. Again, this was provided by Dr. Converse, and he was able to put these age constraints based on sediment from the same core that I was working on. If you look at the yellow squiggly line on top, that's diatom size, and that was provided by myself. If you look at the blue squiggly line on the bottom, you see diatom abundance, again provided by Dr. Converse. If you look at the blue shaded rectangles, those represent glacial periods, and then these unshaded regions represent interglacial periods. And so during interglacial periods, you actually do see what we would expect. The abundance is higher versus these glacial periods. And then there's a really nice correlation between the peaks and valleys of this abundance, as well as with my diatom size. And so that really lines up with the hypothesis with more iron input and iron availability in the ocean. It's really when it comes to these glacial periods that the data gets a bit messy. So if you look at the abundance, you see that it flatlines, and that was really apparent in the smear slides. When you look at this period here, you see some really messy and really high peaks and low valleys. And compared to 50 diatoms per slide, which I was able to achieve in the rest of this data set, at some points I was only to get 2 or 3 diatoms per size. And so this could contribute to this such extreme peaks and valleys, but it's honestly really hard to say because this pattern is apparent further down the line. And so these peaks and valleys and this noisy kind of non-correlating data set between the size and the abundance is not really readily understood or readily explained by the hypothesis that we originally put forth. But that's okay. It's actually good news because this leads to ample opportunities for future research. And so the first thing that I believe that should be done is further analysis of the remainder of core PS 58 to 54. I believe it would be really interesting to see if these really messy data sets from the glacial periods are consistent throughout the remainder of the core, and whether it is or isn't, I think that leads us to some really interesting questions as to the why behind this. And as far as answering the why, to why we had really messy data for glacial periods, I believe that we should look further into biogeochemical cycles during these glacial periods. As I previously mentioned, the global carbon cycle and the global iron cycle really tie into this, and they overlap, and that overlap lies within these diatoms. But I know that diatoms rely on more than just iron and do more than just separate carbon and oxygen. They depend on several variables such as oceanic salinity, temperature, silica content, and because they're photosynthetic, they rely on the sun and climate as well. So I believe taking this a step further and looking into those cycles could at least put us on a track to answer this question. This leads me into my final point for future research, which is looking at diatom productivity, size, and abundance. So right now with this research, what I really looked at was size and abundance. And I say that they should really correlate very well because we know that they both depend very highly on iron. But the very preliminary idea that I had was, is there some sort of variable that can only affect one of these and not the other? So, for example, during glacial periods, is there something that's only affecting size and not affecting abundance? And I really don't know the answer to that. So that's why I'd like to see that done in the future. Finally, I'd like to thank Dr. Jonathan Warnock. He was my advisor through all of this and provided me the opportunity to hop on this research, and he answered countless emails throughout this entire process. Dr. Matthew Comforts, again, just for providing me with all of the data. And then, of course, the IUP Geoscience Department. They just really foster a very supportive community and have done so throughout my entire undergraduate career. Thank you.
All right, thank you to Victoria Lewis for that presentation. Let me scan around the room for questions. Nick Deardorff.
Hey, Victoria. Nice job. I wanted to ask about, in thinking about nutrients, thinking about iron and the different nutrients that are adding to the morphologies of the diatoms, it seems like when they're low nutrient contents, low iron contents, you get kind of short and fat diatoms, whereas when they're healthy, lots of iron, as you stated, they kind of long and skinny. Is the overall mass pretty similar, or are the short and fat ones actually smaller mass? I was trying to determine like what actually drives that difference in morphology. Does it have to do with the crystallization, of the shells themselves? I was wondering if you could speak to that aspect of it.
Sure. That's actually a really good question. By mass, do you mean like the volume of the entire diatom or just the surface area of the diatom?
I was thinking volume, but you could think two-dimensional and go surface area, which should be similar. So either way.
Sure. I actually can't speak too much to that, and I apologize. Other than length and width, I didn't really do too much digging into how the overall volume of the diatom would be affected from these nutrients. Although I would suspect that the entire change in their morphology and their shape would have something to do with being able to gather more iron during these times, if that makes sense.
Yeah, okay. Thank you.
Dr. Hovind.
Hi, Vicki. Hey, I may have missed this on here. There's some audio problems on my side here, but if you go to the slide where you're looking at the changes over time in your records of size and how did you determine that those were glacial versus interglacial periods?
Dr. Matthew Converse, he actually put the glacial and interglacial cycle constraints on this core. I know he used sediment, and I believe biogenic opal was a really big factor in how he did this, but I did not look too much deeper into how he did that.
Okay, so it's based on just the opal abundance, whether it's a glacial or interglacial.
I don't know that it's just opal. But
Okay.
I know that that was a part of his research in finding those glacial and interglacial cycles.
Okay, and then those gray boxed areas then are areas where you weren't able to get 50 samples per slide to measure the size?
No, those areas actually just represent the glacial periods. The only section where I wasn't able to get 50 per slide is just right in between 100 and 200. So throughout the rest of the core, I was able to achieve that goal of the 50 diatoms per size, which is awesome because then I have a reliable sample size. But at some points I was only able to get 2 or 3 diatoms. It was like splitting hairs, just trying to find those 2 or 3. And so I really think that that contributes to this variability, but I can't really be too sure because further down the line, we also see some really extreme peaks and valleys as well.
Okay, thank you.
Sure.
Let me check with Dr. Farnsworth to see if we have any questions from YouTube.
So we do. We have actually quite a few questions. And so the first one is if there's any way to limit when you might be measuring the length and the width of a diatom, but on an angle. So when the diatom's not lying flat.
I'm actually not sure I quite understand the question.
So if the diatom's not flat and you take those measurements, what if they're not straight perpendicular to the microscope ocular?
Yeah, sure. I really don't think that they would present themselves in a way that would allow me to get that length and width. When I was looking for diatoms on the slides, I really looked for these intact and full figures. If it showed anything else, I don't think there's a great picture. You can kind of see like these segments that kind of just look like lines. I don't really know what they are. It's possible that they're diatoms, but either way, I just wouldn't use a diatom that wasn't completely this shape. It just wouldn't be used. I don't know if that answers the question or not.
Yeah, that was great. So the next question is there a particular time period in the core that you think would be beneficial to focus further analysis on? And if so, why?
To my knowledge right now, no. I really only looked at this section of the core mostly due to time constraints on my end, just with like graduating and such. But that's why I really suggest going further into the core and seeing more of these glacial and interglacial periods. Because who am I to say that this really consists, that this pattern consists throughout? And potentially there are some other major climate changes happening that are impacting this iron and these oceanic, this nutrient availability, but none that I know of, really, just because I haven't looked at the rest of the core. I don't know that I could answer that without actually looking at the core, if that makes sense.
Yeah, that's great. I have one more, and I also have the comment that you've convinced everyone diatoms are great, by the way.
Oh, great.
So the last question is have you reviewed any core data from other areas around Antarctica? And do you see similar trends in iron content and diatom abundances in those?
I actually haven't, but I would love to. I guess that could be added to the further research slide. I would love to compare different areas, even around Antarctica. I think that would be a really great exercise for this research, just to be able to compare that. That's a good question.
Thanks.
All right, so now everyone out there knows that if you're looking for something to do, Victoria Lewis has further research for you to do. So you've been notified. All right, I'm going to give the faculty just perhaps a minute to catch up on their paperwork, and then we'll be ready to start the next slide. So I'm not going to cut out my video. I'll just wait here a moment. Our next talk in IUP's 46th Geoscience Day is by Kevin Soffera. I was talking to him earlier this week and happened to ask because I didn't remember when is your talk, and he grimaced a little bit and said, I'm last. And I said, we put you last because we wanted something interesting to finish up the day, and I'm sure that's what we're going to hear. Kevin will talk to us about the record of Terrigenous, glacial, and interglacial variability. I'll let him tell you the name of the core. It's a mouthful. And let's see if Kevin is ready to start.
Yeah, I'm all good.
Okay, I'll turn it over to you and you can lead us into this.
Oops, sorry about that. All right. Hello, everybody. My name is Kevin Soffera, and I will be presenting my senior research project on the record of Terrigenous, glacial to interglacial variability in core KN223-10LC2 along the western flanks of the Mid-Atlantic Ridge. So to get this started, in 2014, the research vessel Nor set sail on its final long coring voyage. The research cruise was originally funded to examine pore water chemistry of sediments that gives information about changes in deep Atlantic circulation. However, while they were out there, extra cores were collected that could be used to address certain paleoclimatic and paleoceanic questions, such as looking at how did the sedimentary components change over time, and what does this tell us about the conditions of the climate or the ocean? What can we learn from the study of dust? So in this study particularly, we're looking at the Pliocene through the Pleistocene, and understanding past processes is the key to looking at current processes. Winds and other kind of climatic factors don't leave a geologic record like most other processes do. So we're going to try to learn how dust can be used as a proxy in understanding how winds and the climate used to act. It's important because wind is related to the oceanic fertilization of wind transported iron as well as ocean mixing. Yeah, that's what we'll be talking about. So the core KN223 and KN223-03 and -10 both rest along the bathymetric high of the Mid-Atlantic Ridge. They're actually on the same site. So although these images say it's 3, it's also 10. They were taken at the same area. So it's on the Researcher's Ridge, a volcanic feature that is off the western flank of the Mid-Atlantic Ridge. The site location is on one of the bathymetric highs just south of the Researcher's Ridge, and it sits on a crust that's approximately 35 million years old. The crew aboard the ship cored the top roughly 30 meters of sediment, and that represents the last few million years of accumulation of this area. So core KN223-10LC2 is comprised mainly of a cyclic variation in carbonate and terrigenous material. There were 3 cores taken at this location: 03LC1, 10LC1, and 10LC2. Those first 2 cores that you see in the green and red lines were cut up to study the interstitial pore waters, which was unrelated to our studies and had to do with the original voyage. But they went back to the site to pick up 10LC2 because the location provided good, complete data of the top 30-ish meters. So if you're not familiar, from top to bottom of the core, it goes from young to old, and there's likely another roughly 60 meters of sediment below that. So the core is carbonate and terrigenous material that follows cyclic patterns. You'll be able to see that more once we kind of zoom in. Both of these graphs were taken on board. Magnetic susceptibility acts as a proxy or way of determining terrigenous iron content, specifically a signal of dilution, so how diluted that content sort of is. Whereas gamma density we're using as a proxy for carbonate content. And so a big part of this process is looking through different glacial and interglacial cycles, which are natural cycles the Earth goes through as a result of astronomical cycles known as Milankovitch cycles. We're looking specifically in this study at the upper 10 meters for a strong glacial and interglacial cyclicity, and that's because those top 10 meters have really strong signals for those cycles. The red arrow you're seeing on the screen points at roughly 18 meters in the core, which is through the transition from the Pliocene to the Pleistocene. So our methods included extracting the top 10 meters of lithogenous material with various chemical baths. This process dissolves non-lithogenous material over many steps and sequences and leaves us only with clays and fine silts, which is what we want. The location of the core in the central Atlantic basin and on top of an elevated feature avoids the coastal input of sediment, as well as any turbidites or underwater currents that may mix up and kind of put the original deposition in disarray or in an order that's not how it was originally deposited. The terrigenous material is therefore assumed to be silicoclastics transported by aeolian or wind-based transport, specifically off the coast of northern Africa and that region. We measure the sample weight and then can calculate the percent extracted, also referred to as the percent dust. This, however, is only the relative input, and without the importance of understanding the time through the core, that's all it will be. So these images are just showing an example of a sample and some of the equipment we use to do this process. Post-processing measurements gives the dry bulk density of samples along the core, and that's what these two graphs are showing. So the top one is that percent terrigenous value, how much extracted per sample we were able to get, and then the dry bulk density is a measurement that's calculated off of the original shipboard measurement of gamma density. And if you notice, you can kind of see somewhat of these cyclic patterns in both of these graphs. The dry bulk density is a little bit more detailed because there's more data to work with, where we're still processing a lot of the samples that fall into this graph. So the next big step is to create a preliminary age model. And the way we do that is we use data from Lysecki and Ramos' 2005 publication of globally distributed delta 18 oxygen isotopes placed along an age model. We can then create our own age model for our location by graphically correlating our gamma density, which is the graph below it, to the curves that they have by using what's known as tie lines. So basically what these red lines show is matching these curves in order to kind of line it up. It's a visual correlation. It's not based on any sort of math or statistics. And obviously there will be more than just these three. I'm just kind of putting those in for example. So using these picks, we can establish a rough time frame for our core down through the depth. So the next thing we do is we can make a linear sedimentation rate of the core. So as you see, the core has changes in its sedimentation rate. It's not something that's been constantly receiving the same amount of input through the last 600 to 7,000 years. It's 600,000 to 700,000 years, excuse me. It's gone through cycles as well, right? And so you can see there's higher peaks and there's lower peaks, but it still follows this kind of up-down cyclic pattern. And it's really important in understanding the accumulation rates, and we'll get into that a bit later, but it's an important part in understanding how age and time relates to our core. So this is the age model that we ended up with. It's what allows our data to be converted from a depth to an age, which is important in avoiding the dilution problem I had referred to earlier, which is that without time, we only have the relative input of components, which can change with variations in dust input or carbonate accumulation. So in order to avoid the issue of dilution and not having the true amount of terrigenous input and understanding how that input changed, we must look at the mass accumulation rate or flux of the sediment input, which requires this age model, as well as knowing how much sediment mass accumulates per area over time. And that's what this graph shows. So this is the dust mass accumulation rate or dust flux, and it accounts for the compaction of sediment that's due to burial as well as dilution effects. So the way we get this is we multiply the percent terrigenous or that percent dust value that we got from extractions by the linear sedimentation rate, and then multiply that by the dry bulk density. So this flux allows us to kind of see the true input of and the accumulation rate of this terrigenous material. We see that it goes through these cycles as expected, and as we are able to kind of collect more data, this will obviously become a more detailed graph with more points that really show detail and intricacy in how it's changed. And then so this next part was then looking at how we can plot different data down an age core, and also how we can relate it to to the glacial and interglacial cycles that we've discussed earlier. So this is the oxygen 18 isotope ratio that we got from Lorraine and Lysecki. Lorraine Lysecki and Maureen Ramo mentioned earlier, compared to gamma density, which is that onboard ship measurement. Note here that these values are in reverse order, and I've just done that to show the correlation. So as this value is higher, you have a lower gamma density, and vice versa. Something to take note of is the shading in these boxes. Gray has an interglacial, or interglacial periods have a gray shading, glacial periods have this white shading. During glacial periods, you see gamma density lower, but this is higher. And then so comparing that to the percent terrigenous as well as the terrigenous flux again, that mass accumulation rate, we can see that both of them are higher generally during interglacial periods. And so it's led to kind of an understanding of how these systems change, and that there is important variability that's recorded in this core. And I'll talk about it a little more in the next slide. But first, flux tells us about the aridity of the regional climate of North Africa. It offers insight into how dusty the area was and how much potential dust-sourced iron fertilizes the oceans. Iron is a source of fertilization for oceans, and it increases biologic productivity. So understanding how differing amounts of iron are entering that ocean can help us understand biologic productivity, which has huge global effects. And so lastly, we also measured size of these silicoclastic dust particles. It's not from all samples, it's from a selection of interglacial and glacial times. But there is a difference between the two. The interglacial average is at 5.28 microns, and the glacial average is at 6.27 microns. So although it's only a micron apart, it is significant because dust size is associated with the strength of winds. It's important because strong winds can impact the vertical mixing of the ocean and change biological productivity, like I've been discussing. Strong winds can also influence the formation of large tropical storms or hurricanes, and obviously the stronger the winds, the larger the dust sizes and grain sizes that can be picked up. So dust size and flux are important to climate modelers because they both factor into understanding how heat moves globally around, as well as how much carbon dioxide is transferred between the ocean and atmosphere through the biological pump. So some things to take away and future potential. This core records incredible climate variability and has a lot of future potential. I've only analyzed the top 10 meters of sediment. There's another 20 below that it's been started, but not to a point to add to this project necessarily. So comparing those two times of data, and then as well as analyzing that transition from the warmer Pliocene to the interglacial and glacial cyclicity that we see in the Pleistocene. And then once we're done with that, comparisons from this core, which is in the Atlantic, to cores from other oceans in the Pacific or the Indian Ocean or wherever it may be. So I'd like to thank the scientists and crew members aboard the final cruise of the research vessel Noor, the Geoscience department at IUP for being great people to be around, especially Dr. Hoven for really mentoring me through this and honestly just putting up with me the past 3 years, as well as financial support that allows me to work on this and so many other people to do research projects at IUP. Thank you, and I'll be taking any questions.
All right, thank you, Kevin. Let me scan around the room for questions. I see Dr. Hoven hands on.
Of course. Hi, Kevin, that was a really good job with that. So it seems to me like the age model development is kind of a rough and dirty way to do that there. I was wondering if you had any thoughts about ways to improve that and maybe clean that up a little bit.
Yeah, sure. So let me move back to that slide. Yeah, it's very much a rough and dirty way of doing it. It's a visual correlation. It's not really based on statistics. There's programs that allow you to kind of match it up in a way where it's tracking different regressions and averages that just wasn't available at the time of doing this. So given more time and the resources available and understanding of the programs, I would have loved to go back and be able to do that sort of quantitative analysis that's not so qualitative and a little bit shaky, but yeah, so it's definitely possible and the options are available.
Okay, thanks.
Thank you.
Let's see, looking around. Dr. Lewis.
Yeah, Kevin, that was great. Appreciate it. You said that the grain size, the difference was significant. You didn't show any whisker plots or any statistics on that, or I might have missed them, but the difference is like a micron. So I was curious about your feelings about the robustness and what kind of statistical treatment would be, or maybe that you've done.
Yeah, it's a great question. I used language that I probably shouldn't have in saying significant. It's I didn't mean statistically significant. There's obviously a lot more sample that needs to be analyzed and grain size analysis that needs to be done throughout the core. I meant to more draw attention to it to say that, hey, there is a difference between the average of interglacial times and the average of glacial times. And I think a future project could definitely get involved with the more statistical side of analysis and really taking a look at if this data is actually statistically significant between interglacial and glacial periods.
Okay, great. Thank you, Kevin.
Thank you.
Let me check with Dr. Farnsworth for online questions.
Yeah, we have a couple here. So the first one is, what is the age range measured in these cores, and how can that window be used to project future trajectories in the model?
Yeah, so the first part of that was the age range in the core, right?
Yes.
Okay, so this is at the top of this core, 0 meters down. That's basically up to present day, or at least present day in 2014. And this goes down through the Pleistocene and into the Pliocene, as I mentioned. This era specifically, the difference is around 2.6 million years, and I don't know right off the top of my head about how far down this would go. So the second part of that question, Katie, could you ask that again?
Yeah. So how can you use that window of time to project future trajectories in the model?
Right. Yeah. So climate modelers are going to be looking at similar conditions that are observed throughout different times of these and comparing it to contemporary times. So when scientists find that our contemporary climate patterns are similar to that of something that's happened before, that's kind of how it's used to extend into current and future climate modeling, is trying to figure out what the future will be like in terms of different parts of or aspects of the climate, and comparing that back to how it used to be and how things were affected as a result of those aspects and changes.
Great. I have one more question from the YouTube crowd, and that is that you mentioned how dust promotes biodiversity. How is that?
So it's not so much the dust, it's a specific element of the dust, being iron. Iron fertilizes the oceans through the growth and development of various microfauna and flora. Various like algae will be able to bloom more if they have access to that iron, basically. So when you have more iron being deposited into the ocean at some rate in some area, and when the iron becomes if it's still the limiting reagent, but that limiting reagent is kind of higher in that biochemical reaction, it allows for the stronger development of these blooms and biologic productivity, since those algae are the bottom of the food web and allow for, as other organisms depend on it through the food chain, it really allows that sort of biologic growth.
Great, thanks.
All right, I'm scanning the group to see if there are other questions in the Zoom room. I'm not seeing any, so I'll thank Kevin for his talk, finishing up a great day. Dr. Deardorff will have a few remarks for us in a minute. Before he does, I want to thank a few people. Our producers of the 46th Annual Geoscience Day will include, of course, Indiana University of Pennsylvania, the Coptic College of Natural Science and Mathematics, and of course, we who are the Geoscience Department. The person I think of as our flight director or in charge of everything is Nick Deardorff. Someone I think of as the chief engineer is Dr. Katie Farnsworth, who's done all sorts of splices and connections between the various online media. This is a narrowcast rather than a broadcast, but it feels like the same thing. And I'm just the talking head or visual face of this operation, the capsule communicator, if you will. I'm Ken Coles, and I got to help these students do their projects for this year. I can't speak for my colleagues yet. We haven't talked about this, but it's been very interesting to have people watch what we're doing on YouTube. And I imagine no matter what circumstances we're in a year from now, we will think about how we can share Geoscience Day with as many of you as possible. Let me see now if Professor Deardorff has something to add.
Sure. Many of you missed my welcoming comments at the beginning because we had some technical difficulties with YouTube. So for those of you on YouTube, I apologize for those, or for our difficulties. Basically, this is our 46th annual Geoscience Day, but it's our first ever virtual Geoscience Day, and there were bound to be some hiccups. As far as I can tell, that was kind of the only one, and it went really smoothly. So I would like to personally thank Dr. Coles for all of his hard work with this, and Dr. Farnsworth for helping get the YouTube streaming up and running and then fixing it on the fly. So thank you very much as far as to both of them. Thank you to all of you viewing. Thank you to the friends, family, faculty, and our alumni that are viewing on YouTube, and then the students and faculty that are viewing through Zoom. We appreciate you zooming in and contributing questions. It's been a really fun and interactive day. Most importantly, I want to thank all of our presenters today. They did, in my opinion, a spectacular job. I was very impressed with the quality of all of the presentations here today. Just as a whole, they were great. I really enjoyed them. In particular, considering our current situation with this COVID-19 crisis, there were a couple questions in YouTube about how challenging was it for the students to put these presentations together to complete their research, having to be at home over these last several weeks. And I'm sure it has not been easy. It's been challenging for all of us, putting classes online, learning online in a new environment. And then also the enormous stress of putting together a presentation for Geoscience Day can be overwhelming. It's overwhelming in any given year. But as I kind of alluded to in the beginning of the Geoscience Day here this morning, we're not going to let something like a minor pandemic keep us from torturing our students. We're going to continue on with such things. But I think the students stepped up very nicely, and I'm very, very proud of all of the presentations. So very well done. And again, I just want to thank one final time Dr. Coles for all of his hard work. I know today went very smoothly, largely because of all the work that he, and then obviously all the work the students put in to this day, into all those presentations. So thank you very much. And thank you again, everyone, for tuning in and participating.
All right, and thank you, Nick, for those kind words. Thanks everyone for joining us, and I hope we'll see you next year. I think that's it. We'll see if people file out. They probably will.